Oh.
Okay, so one of the things that we've done in this class that we did during our minerals unit was we covered the process of going from rocks in the ground to products that we actually use. And this is a process that's important for nuclear materials. Well, for a lot of reasons. One, because it's just chemically and physically interesting how we get from rocks in the ground to nuclear fuel pellets that are in a nuclear power plant. And two, it's because one of the criticisms of nuclear power is that it isn't the nuclear power plant that's dangerous. I mean, we saw the Chernobyl thing, but I've tried to make it really clear that a United States or a modern nuclear power plant isn't as dangerous as a Russian RBMK, and the worries that a lot of people that think about this don't have to do with the power plants themselves, but the fuel cycle, the whole process. Because when you're in a nuclear power plant, as I said, you're talking about a doubly redundant, highly engineered system with a lot of safety protocols. There's a culture of safety in the nuclear industry that I think people don't understand, either pro or anti, that the culture of safety is endemic or a natural part of nuclear science. And, you know, checking and double checking protocols, doing things a very specific way, but that may not be true at all steps where there's nuclear materials. And that's the thing. Because radioactivity is dangerous, because you can't see it, people worry about, you know, what's happening to it in the other parts of the cycle. And so I'll talk about that a little bit today. Not just because of the danger, but it's another reason to know about the nuclear fuel cycle. So okay, of course it starts with exploration and mining. Just like any other process, you start with digging it up out of the ground. And there are, you know, there's ways to find it. Uranium is actually a relatively common mineral. You'll find samples of it in almost any shovel of dirt that you pick up out of the ground in certain types of geology. But more concentrated sources are a little bit less common. We have sources of uranium that are pretty rich in the American West. There's a lot of uranium in Australia. I believe a lot of uranium comes from Africa as well. I'm not 100% sure about that. But anyway, people are mining it, and in fact, that's what I think I told you. Mr. O'Brien, who retired here last year, that's what he used to do. Was he used to go out on Native American reservations and other parts of the West looking for signs of oil, signs of natural gas, and signs of uranium, and that's what he did. He looked at the geology and he tried to get uranium, tried to find uranium, and that's I think he got tired of doing that, and that's why he went to teaching. But I don't want to get into that whole story. And there's a million different ways to mine uranium. You can do pit mining, you can do underground mining, just like a lot of stuff. I'm not going to spend too much time talking about it. There are a lot of things to discuss when it comes to mining. The history of uranium mining in the United States is a pretty colorful one, but I'm not going to get into it right now. Ultimately, then you have to do the milling, and it's a lot like some of the stuff that we did. You're going to take this big pile of rocks, sand and dirt, and you're gonna crush it, and you're gonna process it, and what you end up with is this stuff called yellow cake uranium. And if you look in your book, you'll see it's this sort of orangish powder. You get this yellow cake uranium. That's an orange powder that is if I'm not mistaken, U3O8, uranium oxide U3O8. And this is not the form that's usable. It's radioactive. It's in a powder form. You need to be careful of it, but this isn't the form that's usable. So this is just what we call the milling process, which you're familiar with. That's the first step from mining to purification, and it is purified, but this isn't the usable form. Ultimately, we either want pure metal or we want U2O. And so the next thing that happens is it has to be enriched. I didn't talk about enrichment very much. Let's talk about enrichment a little bit. Okay. In order to get a chain reaction going, you need to have, you need to have a large enough sample of, how am I going to do this? We'll do it like this. Uranium-235 is the only isotope that will split. So uranium-235 is scattered around your average sample of uranium, but 98 point something percent, 98 plus percent, is actually uranium-235, or 238, excuse me. Uranium-238, which is also radioactive, but it doesn't split. And so, let's see, it's something like, there's other isotopes in there. I'm just going to talk about 235. In fact, I'll make 235 red just like I did in my other diagram. The percentage of uranium-235 in your average sample of uranium is about 0.7%. There's other isotopes, as I said, but it's not enough. Like, the vast majority of uranium is 235, and so, or is 238. Why is this important, you ask? I can feel you on the edge of your seats asking this question right now. It's because when I split this atom, I shoot a neutron at this. I assume I've got the neutron going at just the right speed, and it splits this atom, and it sends out those 3 other neutrons. Unless you have what's called critical mass, a high concentration of uranium-235, it's just going to fizzle out. Splitting one atom is not going to make any electricity. You need to split millions of atoms, and you need to do it in a sustained chain reaction. There doesn't have to be enough for every one of these neutrons to hit another uranium atom. In fact, that's what you do when you want a weapon. But what you do have to do is you have to increase the percentage of uranium-235 to about at least 4%. 4% for power. And, well, I just read in the news, maybe you just heard this in the news, they found samples of 27% enriched uranium-235 in Iran. In one of the nuclear power stations, the enrichment plants in Iran, they found 27% enriched. You actually need, well, the rule of thumb is you need about 90% to make a weapon. But people estimate that it's actually, even as low as something in the high to mid-20s might be able to be used for a weapon. Because the point is, okay, let's say I increase it to 4%. Hang in there, folks. I know this isn't the most exciting stuff, but it is interesting in its own way. If I increase it to 4%, then maybe one of the neutrons that splits out will cause another fission, and whoops, I didn't draw that right. And then maybe one of these and one of these, but not all of them. That's what we call a sustained controlled chain reaction. About one neutron per fission hits another uranium atom. Once you enrich to, 90, when you get up to 90%, which I'm not really going to be able to do, but you can imagine that you get to a point where you can't split one atom without the neutrons splitting 3 other atoms, and that's when you get a huge explosion. As it is, you just make heat. Okay. Check something. Am I in the picture here? Just barely. Good. Okay. So that's what enrichment is for. Enrichment is to increase the percentage of uranium-235 so you can get what's called critical mass. You've heard that expression probably. Critical mass means, in this case, it means enough of anything for something to happen. It's like, guys ever been to a party that didn't have enough people, right? Or a dance that didn't have enough people, nobody dances? Once you get past 50 people or something, 30 to 50 people, that's minimum critical mass to get people dancing, Past 12 is enough to get people talking, but past 30 or 40 is enough to get people dancing. Past 100 is when you really have to watch out for holes in the wall and stuff like that. That's when you really got to party. So it's the same kind of thing with critical mass with uranium. Okay, so how do we do it, you ask? That's a really excellent question. It's a process called... I got tape on my fingers, it won't come off. Okay. It's a process called gaseous enrichment. No, it is not. It's called gaseous diffusion. Uh-oh. Okay. I'll do this real quick. He says. All right, if you were to compare an atom, okay, hold on. The first thing, you turn the U3O8 through a chemical process of dosing it with fluorine gas into UF6. I'll make it blue. UF6. Uranium fluoride. Uranium fluoride is a gas. Uranium fluoride, as soon as you turn it into uranium fluoride, turns into a gas. It's just like you can have carbon, like graphite or charcoal, and if you burn it, that turns it into carbon dioxide gas. Sort of like this. You turn this into uranium fluoride gas, and all of a sudden you have a room full of uranium gas. And then what they do, this is, you guys are really going to understand something like 90% of the world, 99% of the world doesn't understand. That's why I love teaching this. So if you were to look at a uranium-235, let's make this a 238. A uranium-238 UF6 molecule and a uranium-235, we'll make this one that color. This is a tiny bit smaller. A tiny bit smaller. Because it's 3 neutrons less. And so they just put them all through a sieve. They put them in a centrifuge that spins around really fast, and in the middle of the centrifuge is a sieve with little holes in it, little tiny atom-sized holes in it, and you've got the mixture over here, and this thing's going around and around and around really fast, really fast, really fast, and what that does is it causes the smaller ones to migrate over here in a slightly larger percentage than the other ones. notice how it doesn't go from 0.7% to like 100%. It's slow. You have to do this thousands and thousands and thousands of times. And after you spin this thing around thousands of times, it separates out the slightly lighter U-235, slightly smaller, slightly lighter. And then you slowly can increase the percentages. I mean, Iran has been doing this for, I think, 4 years now, and they're up to 27. So, because they have a limited number of these plants, they have to hide them from us being able to find them and get at them easily. And so they don't have the tens of thousands of centrifuges that we use to do this. We have a plant in Paducah, Kentucky, where my brother lives. Yeah? Oh, you were waving somebody? All right. I thought you had a question. Anyway, we have a gaseous diffusion plant in Paducah, Kentucky. I think it's closed down now, actually, because of pollution claims. Not to editorialize, but it's to talk about the possible dangers. This is a very dangerous process as far as having to have everything sealed up very carefully, being very careful with your workers. The plant closed down with $73 million in health claims from its former employees against it. Whether, do the research on that yourself, but it's the gaseous diffusion plant in Paducah, Kentucky is the only place this was done that I know of in the U.S. So anyway, so that's enrichment. At that point, it's just made into fuel. This is the last step, pretty much, sort of. So this whole process was enrichment and diffusion. Definitely our most complicated part of the cycle yet, but it is complicated. The last part is fuel fabrication. Fuel fabrication, the UF6 is converted into, what is it, U2O or UO2? Sorry. UO2, uranium dioxide, and it's made into fuel pellets. Pellet with one T, I guess, which is, it's a mixture of UO2 and clay, usually, or some sort of it's a ceramic. It's a ceramic of some sort, and this is what goes into the power plant. I don't think I still have the box. The box has a little sample nuclear fuel pellet, which let me see if I can look up these figures. I'll give you guys a break in just a second. Nuclear fuel pellet is actually smaller than this. The last thing I'll tell you guys is some equivalents for how much power that is. Okay, so a single uranium fuel pellet the size of a fingertip contains as much energy as 17,000 cubic feet of natural gas, 149, was it barrels or gallons? Gallons of oil, or almost 1 ton of coal. So basically, 1 ton of coal is the same as 1 nuclear fuel pellet as the amount of energy that it can release. All right. Why don't we pause there, take a little break, and start up again in a minute.
I'm gonna go see my mother real quick.
I did not hear anything that you just said. I'm sorry.